Hi, and welcome to the next installment of the exponential function test helper videos. I'm going to consider a problem similar to number 2 from the April 2019 exponential functions test. In this problem, in the original test, we're looking at a town which is shrinking in its population over time, and populations tend to grow or shrink, aka decay, in an exponential pattern. So exponential functions are a useful tool for making predictions about how that happens. So we're going to start with a little story about the town of Pittsfield, Massachusetts. I've gotten some data from the U.S. Census. For 2010, Pittsfield, Massachusetts had a population of 131,294 people. And in 2017, that population had dropped to 126,313 people. Over that time, which note is a 7-year time span, the percent rate of decay was about the same each year from 2000 to 2017. So this could be considered an exponential decay for that time period. Now, we're supposed to use this information to predict back in time, to track back in time to 1965 and see what the likely population would be using exponential, not linear tools. We're also supposed to take a look at the population decay. This should be decay in this case. This structure will work for decay or growth. The decay were always the same exponential rate. When did Pittsfield have a population of 175,000 people? That was in the past because it's shrinking. And when in the future would it drop down to 90,000 people, assuming the decay continues to be exponential? All right, so the first thing we got to do in this problem is we've got to set up our basic equation describing the decay of the population of Pittsfield over time using the data we've been given. So we say y equals AB to the X is our basic structure, initial value of A, which we'll have some choices about, B, which is our base, which we'll have to do a couple of tricks around, and X is time. I'm going to propose that X be equal to years, and then we'll have some choices about how we set up X. I'm going to start off by getting the base, because since we have choices about our initial value, but base, we really don't. So we say y equals our initial value a times, and now our base is going to be based on what we multiply this number, our 2010 population, by to get our 2017 population. So to get this to turn into this, the best way to do that is multiply it by our future population divided by our older population, because it'll cancel out our older population and leave our future population alone. So that's going to be 126,313 divided by 131,294, and then we're going to raise it to X over, we have to split that over 2010 to 2017. We're going to split that into 7 times the pieces. Now, if we want our initial value to be the 2010 population, which was 131,294, we can say this, 131,294, replace A with that. And then we can either treat 2010 as 0, or we can do this. Get rid of the X and say X minus 2010. And then in 2010, it will behave as if this is as X is 2010, will behave like the y-axis. So that's one way we could do it, or we could do it another way. Set it up the other way. The other way we can do it is we can just not worry about that and just keep track of the fact that X is that 2010 is our 0 year, I should say. So we can use either version and this will work. So copy pasta that over into Desmos. This is our one approach, and I'm going to have to do some messing around with Desmos to make the Desmos happy with me. Okay, so got that. I'm going to say that over 131294. Get rid of this extra stuff, and then I'm going to do that, and then we're going to get rid of this and just raise this. Parentheses. Raise this to the x minus 2010 over 7 power. Okay, and now one thing you might notice is we have to zoom way out to get to this. I'm going to do a little cheat. I'm going to make that 13 point, and I just have to remember that I made this initial value 100,000 times smaller. And I can go ahead and do this. I can say, okay, well, when y equals 13.1294, I can see that it intersects with the year 2010. So that's one way I could do it. And then there's another way I can do it. I'm going to copy pasta that. And instead of making that minus 2010, I'll just make it x. And now my function goes through 13,000, my scaled down version of 131,294 at 0. I think that'll probably be a little easier to work with, but we can do either one. Okay, so now I've got my basic equation. I'm going to zoom this a little bit so it's a little easier to see, and then I will zoom this. You can do this in the with the little wrench up here in the settings, graph settings menu. If you want, you can change your X scale and your Y scale and what you see on the screen. Okay, so now I've got my basic equation. Yay, that's awesome. Now we got to use that function to figure out some stuff. So one thing we could figure out is what is the likely population going to be in 1965? If you're using the first equation here, what we need to do is we just say x equals 1,965, and we see where it intersects with the function. So in 1965, we would have had 16.835. And I'm going to zoom in a little bit on that. So I'm going to get a little better number. But that population would have been actually 168,350 if we adjust that decimal. So here we go. Yes, I am aware there's some odd artifact showing up on my screen. That's my wife's name. I don't know why that's happening. Don't worry about that. So we can figure out that the population will be 168,350-ish people. And that'll be good enough. 168,350-ish people in 1965. Okay, I'm going to go back and I'm going to do it again using the other equation. So I make that go away. And instead, we're going to go back over here. And that's in the past. So instead, we're going to say, okay, x equals, I'm going to need to know how many years in the past before 2010, 1965 is. So that's an easy way to do that. X equals 1965 minus 2010, which gets me a negative number. And there I have it, once again, intersecting at 168,350 people, minding that I put that decimal there to make it easier to see things. All right, I'm going to stop because Screencastify says I'm running out of space, so we'll stop.